Hello everyone, I am Sr.Stephy from the Department of Mathematics, Nirmala College for Women. Here in this video, I am going to explain about complex functions. What indeed is a complex function? Let us consider a complex plane. Here S is a set of complex numbers. Let us consider Z to be a complex number from S, and we define a function f on S. So we get a function value f of z. So f is a complex function that associates every complex number in S to another complex number in the complex plane. And we denote this complex function by omega equal to f of z. Now we can define single valued function, complex multiple valued function, inverse function, polynomial function, rational function and bounded function in terms of a complex function that is in the complex field. So let us see this one by one. What is a single valued function? A function which gives only one value when the function is defined on that particular set. That is called as a single valued function. So let us see an example. Consider f of z is equal to z square. This is a function defined on S. So if we consider z is equal to 1 plus I, we get the function value f of z as 2i. So other than 2i, we are not going to get any other value. Hence, such a sort of functions are called as single valued function. The next is multiple valued function. When do we call to be a multiple valued function? When we get more than one value. So consider this example, f of z is equal to root z. I'm considering z is equal to 4 cis pi by 4. We know cis is cos theta plus I sin theta. The f of z value, we get two values here. The first value is 2 cis pi by 8 and the second value is 2 cis of pi plus pi by 8. Since we are getting two values, we deem this to be a multiple valued function. The next is an inverse function. So ordinarily we define a function from a set S, that is a domain set, to the range set S dash. Okay, so this is a rule. So it associates values from S to S dash. If at all we are able to find a function f inverse that associates values from S dash to S, in that case this becomes a inverse function. The next is a polynomial function. Let us denote the polynomial function by Pn of z. And if this takes the form a0 plus a1 into z plus a2 into z square plus etc. up to an into z power n with the condition an not equal to 0, then this is the definition for a polynomial function where a0, a1, a2 etc. up to an, they are all constants, and z, z square, z bar n, they are all complex numbers. The next is the definition for a rational function. So the rational function is nothing but r of z we denote. This is a function which is expressed as a quotient of two polynomial functions, that is p of z divided by q of z. Here p and q are both polynomials and the condition is q of z should not be equal to 0. Such a sort of function we call to be a rational function. And the last here in this is a bounded function. What is a bounded function? When you define a function on a set S, there exists a positive quantity m such that it satisfies the condition modulus of the function value should be less than or equal to this positive quantity for all values of z in S. In that case, this function is called as a bounded function. Okay. Next, we are going to discuss about few important definitions in complex analysis. The first is limit of a function. So for limit of a function, let us define a domain complex plane and a range complex plane. So I take this to be my domain set with z0 a point in S. And the z0 is a limit point. Let me take this to be delta. So let me take this as A and this is epsilon. Now consider another point z in S we define a function from S. So here let me take the function value to be f of z, as we already know. Now what happens here is, if for any epsilon greater than 0, there exists a delta greater than 0 in the range set, such that it should satisfy the condition the difference between f of z and a, the modulus of the difference between f of z and a should be less than epsilon for all values of z that we consider in the domain set other than the point z0, with the condition difference between z and z0 should be less than delta. In that case, we say that a is the limit point of f of z at z0, or we can represent in simple terms as limit z tends to z0 of f of z is equal to a. So this is the definition for limit of a function. The next is continuity of a function. For continuity of a function also, we define a domain and a range. So this is my domain set. I take a point z0. So the function I'm defining from S on S. So this is the function value f of z0. If I take a value z here, I get some value f of z. Okay, so how do I define continuity here? Let us consider z0 is a limit point contained in S. So this distance is delta and this distance is epsilon. Let me consider. If the limit of f of z at z0 exists, so in order to define continuity, the necessary condition is that the limit should exist at the point whatever we consider. Here I have considered the limit point to be z0. So limit at this point should exist and it should be finite with the value equal to f of z0. In that case, we say that continuity of a function is here and we can define. So in other words, we say limit z tends to z0, f of z is equal to f of z0 and the value should not be equal to infinity, which means that it should be a finite value. Or in other terms, I can say that for any epsilon greater than 0, there exists a delta greater than 0 such that modulus f of z minus f of z0 should be less than epsilon for all values in Z, for all values Z in S, which satisfies the condition modulus of Z minus Z0 is less than delta. So when the modulus of the difference between Z and Z0 is less than delta, if we are able to find the modulus of the difference between f of Z and f of Z0 to be less than epsilon, in that case we say that the function f, which we have defined on S, is continuous. And since we have considered z0 as a limit point here, we say that the function is continuous at z0. Next, we are going to define differentiability at a point. Suppose we consider a single valued function. So I have defined already what a single valued function is. F in a region. And we have z0 as a point in the region. So we are not denoting at what sort of a point is that. When do we say that f is differentiable at z0? When it satisfies the three conditions below. First, the function value at z0 should not be equal to infinity. That means it should be a finite value. The second condition, limit z tends to z0 of f of z minus f of z0 divided by z minus z0 should exist. And the third condition, that the limit value which we have defined earlier should not be equal to infinity. So under these three conditions, we say that the function is differentiable at the point z0. The next is differentiability in a region. So the earlier definition was differentiability at a point. Here I am going to say differentiability in a region. What is the difference between these two? So let me consider a region. So the point z0 is here. So if it satisfies the above three conditions that we saw in the earlier definition, then we say that the function f is differentiable at this point z0. Now there are many other points here in this region. And if the function f is differentiable at all these points, then we say the function is differentiable in that region. Next is analyticity at a point. So Consider the same example. We have a point z0 here. Now this z0 can have some neighborhoods, okay? So it can have any number of neighborhoods. So if I consider a neighborhood n1, and inside that neighborhood we have so many points. If the function is differentiable at all those points in that particular neighborhood, then we can say that the function is analytic at this point z0. Now consider some point z1 here. And for z1 you have some neighborhood. And if the function is differentiable at all points in that neighborhood, we say the function is analytic at z1. Okay. So remember this concept. I'm going to extend this for the next definition, which is analyticity in a region. So consider the same. I have a point z1, I have a point z0, z1, z2, okay, in some region. So at z0 you have some neighborhood, and at all those, okay, let me consider this is a neighborhood of z0, and there are many points where the function is differentiable. Consider z1, you have a neighborhood, you have so many points in that neighborhood, but at all these points f is differentiable. Similarly, I have so many other points, okay, here in this region. Now at all these points, if the function is analytic, that means in all those neighborhoods it is differentiable, then we can say that the function is analytic in that region. Now I'm going to tell about how to connect the topics of limit, continuity, differentiability and analyticity. So if a function is analytic, it means that it is differentiable. Without the concept of differentiability, we cannot talk about analyticity. If a function is differentiable, it means that it should be continuous. If a function is continuous, it means that limit of function exists. So it is not the other way around. That is, if limit of a function exists at some particular point, it is not necessary that the function should be continuous. It may be continuous or it may not be continuous. Similarly, if a function is continuous, not necessary that it should be differentiable, may or may not be. The same applies for differentiability and analyticity also. But the other way applies. If a function is analytic, it means that it should be differentiable. If the function is not differentiable, you cannot talk about analyticity. If a function is not continuous, we cannot talk to the next step, that is, we cannot talk about differentiability. So I hope that these concepts of functions and limit, continuity, differentiability and analyticity are clear for you to an extent. So thank you for watching.